In the previous module, the boy ran two equal angles A in two separate runs. But what if the angles are not the same? Say on the second run, the angle is 3 times as much. And what if he took a walk and started the second run from a point different from where he finished the first run? Can we still use the rotation argument to justify that D2 will be 3 times as much as D1 because the angle is 3 times as large? It seems so, but let's get our intuition on firmer footing. After ending the first run at X, the boy takes a walk to point P and begins running until the coach signals him to stop after an angle 3A. Let's draw interim markers at intervals of angle A from where the second run begins, which is point P, until it ends. Let's label the points Q and R and S to be at angles A from P to Q to R to S. Now let's rotate until point P is due east. Since point Q is exactly where X is, at an angle A from east, we know that PQ must also be D1 meters. Now let's continue rotating until point Q is due east. Since point R is exactly at X, at an angle A from east, we know that RQR must be D1 meters. Finally, let's continue rotating until point R is due east. Since point S is exactly where X is at an angle A from east, we know that arc RS must also be D1 meters. And PS, which is the total distance the boy ran, equals PQ plus QR plus RS, and each of those we've shown to be D1, so the distance PS must be 3 times D1 as we guessed initially. Now we can guess that in general, the arc length along the circumference is proportional to angle inscribed at the center. And now we are ready to define a radian. A radian is the angle with an arc length of 1 on a circle of radius 1. So in this picture, the blue line is from the unit circle and it has the radius 1. And the purple line, value 1. And if the arc length is also 1, the arc in white, if that's length is 1, then we define the angle between the blue and purple lines to be 1 radian. This is the definition of a radian. Let's apply this definition and ask ourselves, how many radians does a semicircle have? First, we observe that the semicircle has an arc length of pi. The diameter is 2, so the arc length, which is half the circumference, must be pi. And we are trying to ask ourselves, how many radians must have an arc length corresponding to pi? And the answer is, if 1 radian has arc length 1, pi radians must have arc length pi. So pi radians have an arc length of pi, or a semicircle has pi radians. And now we can relate radians and degrees. Pi radians is 180 degrees, or 1 radian must be 180 divided by pi degrees, or 1 degree must equal pi by 180 radians.